force between two bodies having identical electrical charges. It's going to be what kind of force? It's going to be repulsive, correct? Let's see which one fits. A force of repulsion, yeah, that's true. Force of repulsion if the charges are negative, no. We found our answer. Directly proportional to the distance between them. Directly proportional to the distance between them. No. The further away they get, the weaker. It's indirect proportion. Right? So that was wrong. Okay, so A is the right answer. And I'm trying not to look at the answer. It's just there for confirmation. Okay, atoms having equal or nearly equal electronegativities are expected to form what kind of bond? Looks like we have choices here. Well, first you have two types of ionic and covalent, and then the covalents are subdivided into polar and nonpolar. So if they're nearly identical electronegativities, they should be both covalent and nonpolar. Right. Nonpolar covalent. There you go. About 3. You might be able to do all of it. They go this quick. For these elements, cesium, fluorine, chlorine, order increasing electronegativity. Right. So in general, electronegativity does what? Increases from lower left, upper right. Okay. So anything below would be lesser. Anything to the left would be lesser. Right. So in order of increasing, so the least amount, the least would be probably cesium, because it's way down in the lower left-hand corner. Well, that's it. Right. Cesium, chlorine, fluorine. Chlorine is below fluorine, so it's lesser, and fluorine is the greatest. Electron pair in CF bond could be considered what? CF bond. Okay, electron pair. That represents 2 electrons. Okay. Closer to the carbon, because the carbon has a larger radius. No, it's closer to the fluorine, right? It's a higher electronegativity. Closer to the fluorine, because fluorine has, well, there it is right there. It has to be that one. All right. Let's see. 5. Which of the following molecules has no dipole moment? What do we need to know to determine the, they're talking about polarity. What do we need to know to determine the polarity of a molecule? Right? 1. Bond polarity. Right? And what else? Geometry. We need to know how the molecule is arranged. Because if the molecule has polar bonds, but they're equal and opposite one another, they cancel out. So let's see what we have. Carbon dioxide. Like that. So it's going to be polar that way and that way, equal amounts because they're both oxygens. That cancels out. It's nonpolar. Has no dipole moment. How about ammonia? Let's see, it's got one in the back here, got one here, got one here, right? Forms that triangle on the bottom. It's a trigonal pyramid with 2 lone pairs up there. So its total dipole moment is this way. Okay. How about water? Water's like this. Right. Goes this way on the bonds. So the vector summation is like that. So carbon dioxide has to be it. Or is it none? No, it's carbon dioxide. The polar bonds cancel out because they're equal and opposite in direction. Okay, how about, oops, wrong way. 6. Which of the following has the smallest radius? Okay, this is kind of a tricky one because we've got ions here. If it were just atoms, if it was neutral atoms, we would look for the smallest radius would be where? Upper right, correct? The radius increases going down and increases to the left or decreases to the right. So the smallest radius would be upper right if it were pure. And let's see, upper right would be, if these were neutral, upper right would be, let's see, sulfur, chlorine's to the right. But chlorine, now look at chlorine. Chlorine's got this extra electron, which makes it go like that. So probably the smallest ones would be, it'd have to be a positive charge, something. And potassium, you know, that's not even a fair question because we didn't work on ion size except to say that if you make a positive ion, it decreases the size. Make a negative ion, it increases the size. So that's not really a fair question. Even though it's true, potassium is the smallest ion of the bunch. Is what it is. Hadn't noticed that before. Increase. Now here's another one. Arrange these in order of increasing size. Let me see what the explanation we have here. Let's look at 6. Oh, that is tricky. That previous one. Let me go back. Previous one. Isoelectronic series. Potassium, chlorine, sulfur, and argon. Those are all isoelectronic. And then rubidium. Rubidium is way down here. So even though we stripped it of one electron, it's still the biggest because everybody else is way up here. Right? So we can throw rubidium out all right now. It's just way too big, even if it's an ion. So the rest of them are isoelectronic, which means they have the same number of electrons. And which one has the most number of protons? This one. Same number of electrons, more protons. That's how you solve that one. Okay, let's look at the next one because it's ions also. Oops, too far. Come on. There we go. So how did I solve this one? Same way. Which ones are isoelectronic? All but gallium are isoelectronic. Gallium. The rest of them are isoelectronic. Same. So what we do is look at the number of protons to order these guys right here. Then we have to say, how are they related to gallium? So increasing number of protons from calcium, no, decreasing number of protons. Right, we put them in increasing size, so we decrease the number of protons to make them get bigger. So this one has fewer protons, one less than that one. This one's one less than that one. This one's one less than that. Okay. So this is the correct order for size here because of the number of protons, the same number of electrons. So we increase the protons from this direction and it increases, increases in order of increasing size. you know, that's not even answered right. In order of increasing size should be left to right, right? So we'd have to, okay, so increasing size is on this end. So now where do we put gallium? All right, potassium. Gallium is bigger, a lot bigger than these other guys. And one of the reasons it's bigger is it also has d orbitals in it that occupy d orbitals. That's what's balloons calcium. Even though we take away 3 electrons, it's still got a massive number of d electrons. So, well now, okay, this is right here. Sulfur, chlorine, potassium, calcium. But this one has, okay, that's not a good question. Why is gallium? Because it's got all those d electrons. Where did we put them? Well, it does have more protons. That's not a good question. So if I accidentally put that one on the exam, just tell me and I'll give you credit for it, no matter what your answer is.
I probably won't remember that one.
Okay. Yeah, it'll be confusing. So if you're confused, check on it. In the reaction between magnesium and sulfur, the magnesium atoms do what? Become anions, cations, polyatomics, share electrons, crystallize. Magnesium, when you've got magnesium is on way over there on the alkaline earths, and sulfur is way over there in the chalcogens, you know the difference in electronegativities is sufficient to make it ionic compound. So what usually happens with the magnesium, the metals, they lose electrons, right? So
magnesium crystallize would look pretty cool.
yeah, it probably would look cool.
And then you have something you threw it seven. And you put it in water, and it just goes down.
If it were magnesium metal, yeah. I don't know. Now, magnesium metal is very reactive with oxygen. But I don't know about water.
I saw on like some TV show, they put it in snow, and then they did stuff. I think they might have blown on it or something, but it just created little fires so they could try and
Magnesium.
make a whole fire.
Magnesium in water, you say?
It was in like it was frozen water.
That would still work.
Yeah.
Yeah. So magnesium hydroxide, probably. So we need 2 of these. Oh, and then hydrogen. Yeah. And it just needs air and heat from this reaction. And yeah, that would work.
Because it kept on pouring more magnesium in there, and you put there and try to make it go in the fire, and it just made a little hole. You didn't get down as deep.
Was it finely ground powder?
I can't. It probably was because they had to scrape off cave walls because like magnesium still out the cave.
Okay. Yeah, that would work. Okay, let's see, 9. Choose the molecule with the strongest bond. Okay, remember when we form a bond, and these are all diatomic halogens. So you would expect the electronegativities to be, well, since they're the same electronegativities for each pair, then you know it's not going to be ionic. It's got to be covalent. They're sharing electrons. So what determines the strength of the bond? They're all single bonds, so we can't use that, right? It's not single, double, triple comparison. So what we have to look at is how close can they get to each other? and form the bond. Let's see, if we have difluorine, dichlorine. As a general rule, though, the size of the atoms gets bigger as you go down. So what that does is it moves the nuclei apart, and you can only overlap. The overlap is not as complete when you overlap orbitals with the chlorines, and then you go down to the bromines, and then the iodines. So your first impression would be, okay, if they get farther apart here, then as they get smaller, they should get closer together and have a stronger bond. So you would expect fluorine to be the right answer for that one. But it's not, and I'm looking for my reasoning. What's number 9? Oh, and 10. My goodness, it took me that much to explain it. Okay, I was on the right track. Degree of orbital overlap has something to do with the bond strength. The overlap down here is much more diffuse. Okay. All right. Here's the kicker that disqualifies fluorine as the strongest bond. They're getting so small. Let's see if we have big, big, big here, overlap, and then it gets smaller, and then smaller, and then really tiny. What's at the center of these guys? Protons, right? Okay. At some point, you overlap so close together at the nucleus that you get repulsion from both the nuclei and from the electrons, shared electrons. And that negates the effect of orbital overlap that you would get as you move the nuclei closer together. So that's why it peaks out here. Like you have less bond strength here, increases here, and increases there, and it goes back down here. So this is the peak. This is the strongest bond is between two chlorines because of that repulsive effect.
So out of all of them, it's the strongest chlorine is the peak?
This is the strongest, yep.
Okay.
So we can't rely on just one characteristic, the orbital overlap, to explain it. You can, as long as the nuclei are far enough apart, which occurs here. But at this point, they get so close together, they start to repel each other. And that weakens the bond. Okay, which of the following molecules have the greatest bond energy? Well, that's just another way of saying the strongest bond. Okay. Scroll up a little bit. There we go. Okay. We draw the Lewis dot structures for these molecules. Which of the molecules obeys the octet rule? Which molecule I use them to answer? Which obeys the octet rule? So we're saying that since there's only a selection of 1 through 5, that one of them obeys the rule and the rest don't. Okay. So remember when we did boron trihydride? That's it. It's only got 6 electrons. Right. Boron is 3 valence electrons, and then you have 3 each here, so you have 6 total. So once you draw the skeleton, you're done. So it's less than an octet. How about NO2? Let's see, nitrogen is 5, oxygen is 6, that makes 12 there, 17 total. So that's 2, 4, 6, 8, 10, 12. Okay. Let's see. Oxygen doesn't have an octet yet. No, 17, I'm sorry. 12, 14, 16, 17. So we got all of our electrons, but the best we can do is maybe make a double bond on one side or the other. Make a pair of these and do that. Then you got 2, 4, 6, 8, 2, 4, 6, 7, 2, 4, 6, 8. So nitrogen's only got 7 electrons around. It's just one short of an octet. There's another name for that also. This is called a free radical. Anytime you have an unpaired electron in a molecule or an atom, you have a free radical. And these guys are very reactive. You've heard the popular news and literature. Buy our product as a daily supplement and it will rid your body of free radicals. I don't know how many times I've heard that. And it's to, yeah, as far as it goes, it's true. They're usually, when they give you these dietary supplements to scavenge free radicals, they're usually compounds that have double bonds in them. Double bonds are good at scavenging free radicals because you can break the bond, and when you do that, you suck up that electron to make the single bond plus some other bonds. Okay, so SF6, that's going to exceed. SF6 should exceed the octet. Remember when we drew that one in class? Sulfur 6, fluorines. So we have 1, 2, 3, 4, 5, 6 times 7 is 42, and sulfur is 6, 48. So if we put 6 around each one of these, that means 2. That means 1, 2, 3, 4, 5, 6. 6 times 8 is 48. They're all used up, but we've got 2, 4, 6, 8, 10, 12 around sulfur. So that exceeds the octet. How about ozone? So it's what, 6 each? 3 to 18. We've used up 4 of them. 14. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There, 14. So we used up all 14. 8. 2, 4, 6, 8, 10. 15, 16. Wait a minute. 8, yeah, 18. Okay. So how do we make an octet around this oxygen? Let's do that. Or we could do it on the other side, but they're equivalent structures. So now what are we setting ourselves up for? Resonance. Resonate between the two. We don't know which ones. That's an artifact of the valence bond theory. Okay, so that one does have an octet. PCl5 exceeds the octet. So number 4 is the only one that has an octet. Okay, whoops. Zero net dipole moment. Zero net dipole moment. Oh, we should have kept our structures. So what do you have to do to make a net zero dipole moment? Well, you need symmetry if you have polar bonds, right? So boron trihydride is like that. It's trigonal planar. Remember, 3 means trigonal planar. 3 groups. The VSEPR model. NO2. So NO2, and I put an electron there, didn't I? So we got 3. So that's well, actually, This one has a dipole, right? Because it's going to be like this. It's going to have like that, and that. Trigonal planar electronic structure, but geometric structure is bent. So it's going to have a, let's see, I'm not sure, nitrogen should be this way. Except you got an electron here, so I'm not sure which way it's going to go. But it's a net dipole. How about SF6? Well, we had 6 and no lone pairs. So that's octahedral. So SF6 is going to be a zero net dipole. Let's see, this one does, that one doesn't. And this one, I think, has a lone pair. 5. 1, 2, 3, 4, 5. So phosphorus is 5 plus chlorine is 35. 7 times 5, 5, so it's 40. So we have chlorine. So if we have 8 around here, it's 1, 2, 3, 4, 5, that's 40. Right, so there are no lone pairs. This means trigonal bipyramid. Right, so it's like this, like that. So you have chlorines here, and chlorine here, and chlorine here. So that one's no net dipole either. So this one is, let's see, 0 net dipole. This one, that one, and that one. 1, 3, and 5. 1, 3, and 5. Here you go. That's B. Did I go too fast? Are we good? You have any trouble drawing the Lewis dot structures? It's fairly straightforward. And then you use the Lewis dot structure and the BSCPR model to tell you what the geometry is. Okay. 13. Oh, this is interesting. How many electrons must be shown as bonding or non-bonding in the Lewis structure whose skeleton is this? Okay. These are all the atoms that are in this molecule. That's it. These are numbered. That's not how many there are. That's just numbered. Carbon number 1, carbon number 2, carbon number 3, and 4. Okay. So we have it set up like that. Oops. With an oxygen here, there for hydrogens. Okay. Okay. Now we can draw the Lewis dot structure. Let's see. 1, 2, 3, 4, 5, 6 hydrogens, 6 electrons. Carbons are 4 each. So 4 times 4 is 16. Oxygen is 6. So we have 12, 28 electrons, right? 28 electrons. All right. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We need 8 more electrons. Okay, we can't put any more on hydrogen. So we have to start from the outside in. And we've got 8. 1, 2, 3, 4, 5, 6. And then where do you put the 7, 8? The other 2? Or do you spread them out? Well, if we work from the outside in, right, symmetrically, they would have to go here. That's going to present a problem because we don't have an octet here, we don't have an octet here. We do here and we do here. We got to get an octet over here somehow. So instead of putting the electrons there, let's put them over here. Okay. Now, what if we took those 2 electrons? If we put them over here in a double bond, that would give you an octet here and an octet here, but it would rob this one. So let's put them on this side. Okay, now we got 2, 4, 6, 8, 2, 4, 6, 8. 2, 4, 6, 8. Now we're good. Actually, you're getting a little organic chemistry here. All right, so to answer the question, how many electrons must be shown as bonding or non-bonding? Actually, we didn't have to do that. Right. We just need to count up the electrons. And there was 28, correct? I was answering the wrong question. I think there's another question in here that does need that structure. The next one. Yeah. How many electrons are shared between carbons 2 and 3? 2 and 3. We're sharing 4 electrons, 2 for each bond. So we do need this structure to answer this question. 4 electrons shared right there. Hope I don't need this again because I'm going to erase it. Okay, which of the following molecules contains a double bond? Well, we've drawn the structures before. We know water doesn't have any double bonds. We know nitrogen, ammonia doesn't have any double bonds. Carbon dioxide has 2 of them. Right? You just need to draw the Lewis dot structure and you got it answered. In the Lewis structure of ICl2 minus, how many lone pairs of electrons are around the central atom? So let's see, ICl2 minus. Got 3 times 7 is 21, plus 1 is 22, right? 22 electrons. So we have iodine in the middle, and chlorine on either side. Now this defies, remember the rule of thumb? You need to figure out which one's your central atom. Right? You usually put the more electronegative in the middle. Well, chlorine's the more electronegative. But since we got 2 of them, I think it's better to be symmetrical rather than electronegative. So that's why I put iodine in the middle. Plus, that's the way it's written. Okay, so we've used up 4, which means 18. So that's 6, 12 extras used up, which is 6. So now I can put 1, 2, 3, 4, 5, 6. Okay, so how many, what does it say, lone pairs? Yeah, lone pairs are around the central atom. We got 1, 2, 3 lone pairs. What electronic structure would that be? 1, 2, 3, 4, 5. Trigonal bipyramid, right? What would the molecular structure be? So if we put iodine in the middle, where are the lone pairs going? On the triangle. And the chlorines are like that. Now, you would think that if we put the lone pairs on either end, that would put them farther apart. But we need a symmetry, a balanced symmetry. This works better that way. Plus, these chlorines are big atoms, right? We crowd them together on this triangle or put them way far apart. That works also. So combination of electronic symmetry and steric symmetry with the atoms favors a linear molecule. So this one would be nonpolar. Oh, what did I forget? That right there. Without that charge, this does not compute. Okay. All right. See how we come. We're only on 17. Time's the lab start at 3.
2 hours.
Okay. Wait. Yeah, okay. We can do that lab in 2 hours easy. Okay, 17. Which of the following has an incomplete octet in its Lewis structure? Incomplete octet. That means less than an octet, correct? All right. So we have to draw all the structures again. Sulfur dioxide, sulfur in the middle, oxygen here, here. Sulfur and oxygen are all the same, so it's 3 times 6 is 18. So 2, 4 means 14. 2, 4, 6. 2, 4, 6. That's 12. So we have 2 left over here. So all we have to do is just, we don't want to take this one and make a double bond. We'll take one of these and make a double bond. Okay. That'll still give an octet, octet, octet. So sulfur dioxide is okay. ICL, we got 7 and 7, 14. Two, 4, 6, 8, 10, 12, 14. That's good. Carbon dioxide, we know that one already is good. Right, those are octets are good. Fluorine's good. I bet that looks like a good candidate. So nitrogen is 5, oxygen 6, that's 11. We minus 2 is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 2, 4, 6, 8, that's already got an octet. 2, 4, 5. What if we made a double bond here? Still give us an octet. 2, 4, 6, 7. Okay, there's no way we can make an octet out of that. Right. So this is the one that's short. Nitrogen monoxide. Let's see. Consider the following. Must be for number 18. That fifth given statement. So, which of the following exhibits resonance? Molecules of fit. Oh, is that one out of place? Ammonia, PCl5, water, and O3. Yeah, I don't know what it belongs to. I think when I put this thing together, cutting and pasting, I missed that one somehow. So we can ignore that statement. Just keep going. Which one of these exhibits resonance? In order to have resonance, you need what? You need 2 or more equivalent Lewis dot structures.
We kind of did this earlier, and you used O3 as the example for that.
Oh, yeah. Yeah, okay. So we can move on. As long as there's no questions. How many resonance structures can we draw from the molecule O3? 2, right? Because there's 3 molecules, you could put a double bond over here, or you could put it on this side. That's it. 20. Which of the following types of molecules always has a dipole moment? Okay. Always has a dipole moment. Linear molecules with 2 identical bonds, never. If the bonds are identical, even if they're polar, they'll cancel each other out. Tetrahedral molecule, 4 identical bonds equally spaced. Nope. Trigonal pyramid. Trigonal pyramid molecules, 3 identical bonds. Trigonal pyramid. How do you get a trigonal pyramid? There's nothing in the middle. So the bond has to be with some element up here. And then you have to have at least a lone pair up there. So that one is probably always polar. Trigonal pyramid with 3 identical bonds, right? Because this is not a regular structure that you can get out of well, okay. A trigonal pyramid is derived from a tetrahedron. Like that. And then the central atom, whatever it may be, X in the center, if it's bound to those 4 with equal bonds, then it's nonpolar. But if one of those is a lone pair, then we get a trigonal pyramid here, not a tetrahedron. So that one is always polar because you've always got that lone pair up there. And that's a negative, that's a huge negative cache of charge that drives it this way. Trigonal planar, nah. Trigonal planars always cancel out. So this one right here would always give you a dipole moment, simply because of where its origin.
Oh. We use our periodic table slide on this.
Probably. Yeah. Which set contains atoms listed in order of increasing electronegativity? So the more electronegative, oh, wait a minute. This is okay, increasing from left to right, but this one is backwards, and that one's backwards. Well, it can't be this one. Fluorine's the most. Right. Can't be that one. Could be this one on that far end, or this one on that far end. This one can't be this one. That's on the small end. So it's got to be this one, or that one. Now we need to look at the ordering. Oxygen, sulfur, silicon. Okay. Oxygen, sulfur, silicon. That could be. Yeah. Decreasing from here to here to here to here. Oxygen, sulfur, silicon. Or nitrogen, oxygen, chlorine. Chlorine. Nope, it's going backwards. Can't be that one. How about this one? Phosphorus, nitrogen, oxygen, then fluorine. Phosphorus, nitrogen, oxygen. That's a good one. Phosphorus, nitrogen, oxygen, fluorine. From lower left to upper right. What about this one? We looked at this one before. Is silicon the least electronegative? And then you move to sulfur, then you go up to oxygen. You know, that one could be also. The only way you could break the tie is actually look at the numbers. Now, the answer given here is boron, is B, or 21.
They're closer than B is because sulfur and silicon's further apart than what phosphorus is.
Okay. 21. Sometimes I have to look at my own explanations to see what I was thinking. Sulfur and silicon are reversed, maybe? No, sulfur and oxygen. Sulfur. No, I would expect sulfur to be less than oxygen. Yeah. Silicon to be less than sulfur. That's a puzzlement. Without actually having the numbers, I can't guarantee that this one isn't a good answer too. This may be the best answer, but still.
I would say B is more right because it's closer. It's the only thing I can think of.
Yeah, okay. Well, there you go again. If you stop to be confused with this one, ask me. if one like that occurs. Okay, that's the caveat. Which choice has the bonds listed in order of increasing bond strength? Increasing bond strength. Okay. Well, we know that if you have the same atoms bound together and you go from single to double to triple, that's an increasing strength, right? This one right here. This one's going to be lesser strength than that one, but this one's going to be greater than both of them, right? We already looked at that one before. So that one, that's wrong. That's out of order. CC bond is greater than N2. No. N2 is a triple bond. So CC is less. So that one can't be it. So it's either this one or that one. So let's see. The hydrogen's getting farther away. Oh, no, that's reversed. But at least this one is reversed. Okay, so this one has to be it right here. Go from single to double to triple. That would increase your bond strength or bond energy. Okay, in the gas phase, which of the following diatomics would be the most polar? So what you need is the greatest separation on the periodic table from one another. Cesium fluoride, that's about as far apart as you can get, isn't it? I mean, I'd stop there. Sodium fluoride, that's pretty polar, but cesium is even farther away. It's like 0.7 versus 4.
Basically, if any of it, unless it has FR, then it's cesium.
Yeah. I'm not sure about francium. What is it? It might be pretty close to cesium.
Right below it.
I don't have the, let's see. Ah, here we go. Okay, it's not printed too small. I might be able to read the electronegativities off of it. They're the same. Cesium and francium are exactly 0.7. Okay. So we found our answer. Cesium fluoride is the most polar. In fact, it's probably ionic. Well, which of the following bonds would be the most polar without being considered ionic? Okay. We got to throw out the ionics, and we have to throw out the nonpolars too. Well, they would fit the most polar. Okay, so ionics, throw that one out. Magnesium oxide, oxygen, that's a polar bond. Silicon oxygen is probably far enough apart to be polar also. Okay, so the most polar, throw this one out. Carbon and oxygen, nitrogen and oxygen comparison. Carbon and oxygen is further apart, so it'd probably be this one. Excuse me. Most polar without being considered ionic. Most polar.
Silicon would still be polar. Because it's not too far below. That's right. It's just a row below.
Yeah. Okay, I guess that's all right. Silicon is a non-metal. That's a metalloid. That's a bad question, I think. You could say that, but it's kind of iffy. I mean, when I think of silicon and oxygen bond together, I'm thinking of silicon dioxide, sand. And that's definitely a polar, ionic compound.
It's 6 elements away.
Yeah. But is it so far away that it's ionic? Let's look at this again. There's that chart. Silicon is 1.8 for silicon. Oxygen is 3.5. So that's 1.7. That's ionic. Right, 1.5 is the breaking line. So that's a bad answer. I think it should be this one right here, B. Don't you? Theoretically speaking, which of the following ionic compounds has the largest lattice energy? In other words, the lattice energy most favorable to a stable lattice. All right, how do we approach this? Well, when we're talking about ionic compounds, two things, I think we covered this in class. Two things contribute to the strength of the ionic bond. One is charge number. And the other is radius. How close are they together? So if we look at that and we say, all right, let's see, barium is okay, right? This is -2, this is +2, -2, +2, -2, +1, -1, and they're big, so they're very far apart. Sodium, +1, -1, but bromine's pretty big. And barium and sulfur are +2 and -2, but they're big too. Barium is huge. Sulfur's pretty big as a negative ion. So we throw that one out, throw that one out. It's easy, might throw that one out. So it's really a toss-up between these two, barium and beryllium. Barium's too big. Right? Beryllium, they're the same charge difference, but beryllium and oxygen are closer together because beryllium is a really, really small ion. Yeah, that's why I would say beryllium oxide is probably the most stable because it has the lowest potential energy when they get really close together. Okay, 26. 26. We're about halfway, aren't we? The first electron affinity value for oxygen is unfavorable, favorable, and the second electron affinity value is favorable, unfavorable. All right. The first electron affinity value for oxygen. Let's look at the structure of oxygen. 8. So 1s2, 2s2, 2p, 4. Yeah. So this one is like that. Okay. And the electron affinity means we have to stick another electron in there. Okay. So the first electron affinity, would it be favorable or unfavorable? Well, it's only got one of these two places to go. Is it unfavorable? Then it's favorable. I don't follow the logic there. Maybe I'm barking up the wrong tree. That's possible. 26. All right, that's kind of a squirrely answer. Okay, here's what I was thinking when I wrote that. Electron affinities generally become stronger as we go from lower left to upper right. Okay, that means they become more negative or exothermic. So the first electron affinity should be exothermic favorable, so it's one of these. But the second one is usually unfavorable, trying to add another electron in there simply because Now, before this is neutral, but now it's got a negative charge on it, which is going to repel electrons that approach to be added. So that's why the second one should be unfavorable here. But we know that when oxygen enters a chemical reaction, it goes for a -2 charge. So it gets both of them. But in that scenario, there's something else on the other side pushing those electrons off, usually a metal or another oxygen. And to complete so there's a balance there. Here we're just talking about the separate atom attracting an electron. For the charge on the ion, we're talking about interacting with some other element in the process. So two different scenarios there. Let's see, if there's scroll that one down. Use the following reaction data. Calculate the energy of an HF bond. Let's see if I can do this without looking at my notes. The energy of an HF bond. So what we need is to take an HF gas and separate it. Right? How much energy do we have to put in to make that happen? Does that look reasonable? This is our target equation. So we got to add those together to get that. So let's see. We got an HF here, but it's on the wrong side. So if we take this one and flip it, and then take half of it, then that would change this sign divided by 2. Right? So it'd be 1, 2, no, 2, 7, 1. So it'd be a positive 271 here. So that would give us HF on that side. But it would also give us half H2 on this side. Okay. What about this one? We need an H only on this side. We've got a half. Well, that's a half of H. Okay, I'm going at this wrong. More complicated than I thought. Okay, yeah, okay. That was, I had the right idea. The target equation is correct. If we're looking at the energy of the bond, it needs to be a gas, so we don't have any phase interferences. Right? So the energy of the bond, the target should be this one. Gas yields H gas plus F gas. Okay. So I was right about that one. So we need to flip this one and take half of it. So where did I say that was? 271, right? 271. And the equation that comes out of that this one is HF gas on this side yields 1/2 H2 gas plus 1/2 F2 gas. Okay. Now I need to get rid of the H2s. So the H2s on that side, we'll put an H on this side. So 1/2 of this one puts 1H over here. So I take a half of this one. And that yields 216. No. 216. And it's okay the way it is. So that gives us 1/2 H2 gas yields H gas. Okay. And this one, do the same thing to that. So we take a half of it. And that would leave us with 77. And then that would be 1/2 F2 gas yields F gas. So far, so good? Okay, so this 1/2 cancels here, here. This 1/2 cancels here and here. That leaves us H gas, F gas, and HF. So we just add these together. So it'd be 13, 14, 1, 8, 9, 16, and 1 and 4 is 564. There it is. Okay. Let's see, we need to stop at 28. As indicated by Lewis structures, which of the following would probably not exist as a stable molecule? Well, we can shorten the process. We know methanol is stable, right? CH3OH is methanol, so that's good. CH2O is formaldehyde. We know that was good. This one's acetylene. Well, that was good. It's between these two. So CH3O, how about that? So it's carbon is 4, then 3 each, 1 each for hydrogen, and then 6 for oxygen, which is 13. So carbon, 3 hydrogens, and an oxygen. So it's 2, 4, 6, 8, 5. 1, 2, 3, 4, 5. That's not very stable. It's got 2, 4, 6, 7. It's got 7 electrons there, so that was not too good. How about this one? C3H4. And H4. Just put them where we can. 2, 4, 6, 8, 10, 12. So it's 1, 2, 3, 12, 13, 14, 15, 16. So we need 4 more electrons. Like that, maybe. Okay. Let's see. This one's already got an octet, so we would have to put these 2 over here. And then these 2 over here. There you go. That would work. Right. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. It's kind of like a sequence of acetylene is like this. So you just take this one off and add a carbon with 3 hydrogens on it to make this one. And this one would be, let's see, this is acetylene. There's another name for acetylene is it's an alkyne. Ethine. Ethine is another name for acetylene. It's based upon ethylene here, the 2. And this one would be propine. Trying to remember my nomenclature for organic compounds. Yeah, this would be propine, this would be ethine or acetylene. So yeah, those are stable. So the only one that's not good is this one right here. Let's see. '28, '29, let's see. And I just scroll a little bit. Using the following electronegativity values. Okay. That's nice. Give us these values. Select the following group. Select from the following group the molecule that fits the given statement. The molecule contains a carbon atom with trigonal planar geometry. Oh, we probably don't even need that. Trigonal planar. Trigonal planar. Okay. That first one has this carbon bound to another carbon and 4 hydrogens. 3 hydrogens. So that was tetrahedral. How about this one where we go, this oxygen here? No. Carbon, oxygen. That hydrogen is here. Yeah. That's trigonal plane. I think. Carbon dioxide we know is linear. CH3Cl is tetrahedral. It's got three hydrogens and 1 chlorine bound to that carbon. This one has a carbon bound to a carbon and then 3 hydrogens each on each end. This is ethane. So this is tetrahedral. This one's tetrahedral. This one's linear. And this one is tetrahedral there and trigonal planar right there. So A is the trigonal planar one. Did that one make sense? Okay. D, as indicated by Lewis structures, which of the following species could probably not exist as a stable molecule? Here we go again. We know ammonia is good, right? We don't even have to do that one. How about this one? N2H2. One of these is hydrazine. I think it's this one. It's hydrazine. Well, let's see. N, and then hydrogens. Okay. So we got nitrogen is 7, 14, 15, 16. We've got 2, 4, 6, so we need 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we could put 2 over here. No, let's put 2 over here. That'll be 2, 4, 6, 8. No, that won't work. How about these 2? Now that one's, I don't think that one works. B's the answer. No, D's the answer. N2H6. How would we get this one to work?
You said B whenever you went to number 30 instead of saying what number it was. You said, all right, B. And total.
Oh, okay. So this one's supposed to be valid? It could be like that, maybe. Does that get it? 2, 4, 6, 8, 10. 1, 2, 14. Oh, no, I'm sorry. That's 5. 10 and 2 is 12. 2, 4, 6, 8, 10. And then we would have maybe 1 here and 1 here. No, that's not right. Nitrogen is 5 each, so that's 10. 2 is 12. 2, 4, 6, 8, 10. I don't know how that one would be stable. It wouldn't have the right octet. Try that again. 10 and 12. Nitrogen, nitrogen, hydrogen. 2, 4, 6. 6. 1, 2, 3, 4, 5, 6. So each of those nitrogens would have to have an extra electron on it. Yeah, that one doesn't compute either. Let me see what I was thinking when I answered that one before. Two, 4, 6, 8, 10, 12. It doesn't need a triple bond, it needs a double bond. Okay, that one works. N2H6 would exceed the octet. N2H6. One, 2, 3, 4, 5, 6, and 10, 16. 2, 4, 6, 8, 10, 12, 14. So we need 2 electrons. So we'd have to put maybe one here and one here, or maybe a pair there. Okay, that would exceed the octet on nitrogen, which does not have d orbitals available. Right? That would be unstable. All right, I don't like that question either. 31. Which of the following has a Lewis structure most like that of CO3 2 minus? CO3 2 minus. So this is 4 and 18 and 2. So it's 24 electrons. Oxygen, oxygen, oxygen. 2, 4, 6. 18. 3, 4, 5, 6. 3 times 6 is 18, isn't it? Two, 4, 6, 8. 3 times 8 is 24. Okay. Okay, we've got to make an octet out of carbon. So we could take one of these, make a double bond here. Or we could take double bond there, double bond there. So we got 3 equivalent structures that have to resonate with that one. The carbonate ion is stable. It's fine. Most like that is CO3 2 minus. Okay. SO3 2 minus. SO3 2 minus. Oops. So sulfur, actually it's the same number, isn't it? Sulfur not, oh, carbon. Sulfur is the same as oxygen. So it's 1, 2, 3, 4 times 6 is 24, 25, 26, 26 electrons. So even if we put, there we go. We have 24 and then we have these 2 over here. Right. So that would be stable, right? Octet around everybody. But it doesn't look like that. So we got to find what it looks like CO3 2 minus. NO3, NO3, and it's a single minus. So nitrogen is 5 and plus 18, 6. Plus 18 is 24. I think we got a good candidate here. So it's 2, 4, 6, 8. 3 times 8 is 24. We're good there. Then we have to make an octet. Okay. NO3 minus looks like CO3 2 minus. That's our answer. And since we don't have any squirrely ones, like none of the above, two of the above, one of the above, yada, yada, yada. And once we find the answer, we're done. Okay, 32. Oh, like this marker.
When you were in grade school, and it would get cold in the winter time, they turn the heaters on, and your heaters ever make you have to go out there for a little while because they have black smoke come out of it?
No, never had that happen.
I did a lot whenever I was little.
As a kid, I think we all had hot water radiators in the classrooms.
I don't know, in our classrooms, I guess the Board of Education worked them, and every winter they turn them on, and they ain't been on all year. So they have all them dust bunnies and stuff in them, so they can burn them all up, and then the smoke come out, and it stinks, so they do have to go out there.
Yeah, I can believe that. Let's see. Maybe this color will work. Select the molecule from the following that has a dipole moment. Okay, CO2 we know doesn't have one. That one doesn't have one. Beryllium dichloride, right? This is going to be beryllium's 2, and each one of these is 7. So it's 14, 16 electrons. 2, 4 is 12. 6, 12. Okay, that's a linear molecule with less than an octet, but it still has no dipole moment because it's linear. SF4 that has a dipole moment. SF4, let's see. S, F, F, F. Okay. Sulfur has 6. Fluorine has 7 each. So that's 4 times 7, 28 plus 6 is 34. Okay. 2, 4, 6, 8 is 26. Okay. So 2, 4, 6 times 4 is 24. We have 2 electrons left over. So we have 5 groups, which means trigonal bipyramid. With sulfur in the middle. And then we have 1 lone pair. It didn't say that usually goes on the triangle. And the rest of them are fluorines. So what's that? That. Seesaw. That's a seesaw. That would be polar because fluorine is very electronegative and it's not symmetrical. So we found our answer right there. Xenon tetrafluoride, we did a problem that said that one is square planar because it was octahedral, except that it had 2 lone pairs on it. And SeO3, selenium, I think that's trigonal planar because selenium has 2 lone pairs on it also. Or, no, maybe it doesn't. Selenium is 6. 4 times 6 is 24. Selenium, oxygen, oxygen. 2, 4, 6, 18. So 6 times 3. 6 times 3 is 18. Oh, that's it. It's trigonal planar. Right, so it's non-polar. The only one with a dipole moment is SF4. Choose the statement that best describes PbCl4 molecule in the gas phase. PbCl4 in the gas phase. Okay. Where's lead? Looking straight at, there it is, lead. It's got 2 4-valence electrons. 4, this has 7 each, so it's 28, 32. Okay, so PB, 1, 2, 3, 4. 2, 4, 6, 8 is 24. So 6 times 4 is 24. That's it. It's tetrahedral. So a bond angle of about 109. Okay. All right. We're getting there. I need to get the marker. I forgot it around. Yeah. Which molecule has the largest bond angle? The largest bond angle. What would be the largest bond angle in a molecule? Well, we know tetrahedrals are 109.5. We know trigonal bipyramids and trigonal planars have 120 and 180. Linears are only 180. So the largest bond angle would be a linear molecule, wouldn't it? Would be, unless we could find a trigonal bipyramid or a octahedral. So let's say linear. That's not linear. No, because we've got it's bent actually. How about this one? OF2. Oxygen still has 2 lone pairs, it's just like hydrogen's there. That one's bent, that one's bent, that one's bent. This is linear. I have this like that. So that angle is 180 degrees. So C is the best answer for this one. And we can't say more than one of the above have equally large bond angles because this one is linear and the rest of them have less than linears because they're all bent. Which of the following molecules is non-polar overall? Non-polar. All right. We'd have to draw the structures. If we work from the bottom, OCl2 is bent. That's polar. H2S is bent. That's like water. Right? Sulfur and oxygen are from the same family. So that one's going to be bent. This one's tetrahedral. That's definitely non-polar. SF2. What is that one? SF2. Sulfur is 6, 7 each there, so that's 14, 20. So that's 6, 12, 8, 1, 2, 3, 4, 5, 6, 7. Oh no, I'm sorry. Hold on a second. 20 total, right? 7, 14, 6. Okay. 1, 2, 3, 4, 5, 6. 7, 8, so it's 16. 16 if I put all the way around. It's 4. Okay. 1, 2, 3, 4. Okay. That was going to be tetrahedral, electronic, and bent. Okay. So that one would be polar. How about SF4? So we got 7 each year, so that's 28, and 6 is 34. Okay, so if we put 6 around each one of these, that makes 8 around each one. 4 times 8 is 32. So we got 2 left over. So that one's going to be electronic, would be 5 trigonal bipyramid. So that one would be polar also. All right, so the only non-polar in there is carbon tetrachloride. Let's see, 36. I better be more selective for the rest of them. How about we got a bunch of these. Okay, we can do 49. Which of these members, I guess it's 1, 2, 3, 1, 2, 3. Which one is more metallic? The more metallic would have the lowest electronegativity, but also the lowest ionization energy. That would be barium. Right? The more metallic means it gives up its electrons much more easily. So barium for that one. The more covalent would be, well, a metal and a non-metal, or a non-metal, non-metal. That's definitely covalent. And highest electronegativity. So oxygen. And so barium, nitrous oxide, and oxygen. There we go. It's E. Let's see. Use the bond energies given below to calculate the enthalpy change for the reaction. Okay, can do this one. What we have to know is the bonds that are being shown here. HCN. Okay. H2. CH3. Like that. Yeah, that's right. Okay, so what we need is add up these bonds and subtract these bonds. So what do we have here? We have a carbon hydrogen. Carbon hydrogen, 413. We've got a carbon triple nitrogen, 891. Okay. We have a hydrogen, 432. Right. So that's, oh, we've got 2 of them. So this is the energy it takes to break all those bonds. 891 and 432 times 2. So I get 2168. And then the bonds that form are, let's see, 1, 2, 3, 3 CHs. And 1 CN, 305, and 2 NHs. 2 times 3, 91. Okay. 413, 2 times that one, 305, add together, and 391 times 2, and add that one in. 1913. We'll subtract this one from that one. And we get 255. But, uh-oh, what did I do wrong? (413) CH. Yep. C double bond N 891. Yes. 432 times 2. See if I add those up right. $21.68. Okay. 3 CHs, 413. And then 305 for the carbon and nitrogen. And then 2 nitrogen hydrogens. Oh, 2326. That's where I get. Minus 158. B. So it's an exothermic reaction. All right. 50, we're going to get close. Given the following information, calculate the change in enthalpy for this one. This is a case where we're gonna do Hess's law again. Add these things together to make the, so unless you want to, we'll just skip that one. 52, that's the last one. No, there's a 53. 52, select the lattice energy for rubidium chloride from the following data. In order to do this one, we have to understand what those terms mean. So we need to stop at this one for just a second. Find a marker that works. Okay. Well, this one is the energy it takes to sublimate the rubidium from solid to gas. Okay, that's self-explanatory. Ionization energy. Ionization energy for rubidium would be this equation. Gas yields. That's what that stands for. BE for this one, bond energy. So this one would be Cl2 yields 2Cl. And these have to be gases. And then this one is the energy, the enthalpy of formation for rubidium chloride. So remember that one, rubidium chloride, most stable is a solid. And then you would form that from rubidium solid because it's a metal. And then chlorine gas, because that's the most stable at room temperature and pressure. So we need half of this one. So that's the equation that goes to this one. And electron affinity for this one is chlorine gas plus an electron yields chloride ion gas. So those are the equations that fit each one of these. Now you have to make them fit the lattice energy. And remember, the lattice energy will be rubidium ion gas plus chloride gas yields rubidium chloride solid. That's your target equation, derived from all of these. So the real trick to this one is to understand what they mean by each one of these. Once you know that, then it's just Hess's law. And it should be minus 695 is the lattice energy. Okay. Let's see. We have some fill in the blanks things. Yeah. Okay. Well, obviously this came from my other course because I'm referencing Zumthor's textbook. But there should be a section in there that covers this for Brown as well. In spite of the larger electronegative difference between the bonded atoms of beryllium and chlorine, the beryllium chloride has no dipole, while sulfur dichloride does have a dipole. So what's the explanation? We just go back to, we already know the bonds are electronegative, right? So it has to be something with the geometry. So the geometry of beryllium chloride is linear, which means the dipoles cancel out. And the SCl2 has a tetrahedral structure geometry. And when you look at the molecular geometry based on that, the molecular geometry is bent. So the vector addition there gives you a dipole. Okay. All right, and I think this is the last one. Draw the structure. Yeah. Draw the structure, the Lewis structure for iodine tetrachloride -1 ion. And then say what shape is it and whether it's polar or not. So you just have to draw the structure. I just did it this way because I could. With these guys going to the back and these guys coming out in the front, that's what the solid line means, and the dashed line means it's going backwards. So basically what you have is, and don't forget that negative sign. Basically what you have is a octahedral, 1, 2, 3, 4, 5, 6, an octahedral electronic structure, but these lone pairs are at the apex. So this is a square planar. That's the molecular geometry. And because of that symmetry, it's nonpolar. We've got 7 minutes to spare. Okay, any questions, comments, complaints?